Anyway, let's talk about L'Hopital's rule. So here is the statement. If the limit as x approaches a of f of x over g of x is either a 0 over 0 or some sort of infinity over some sort of infinity. It doesn't matter what sign of infinity, meaning it can be positive on top and negative on the bottom. It can be positive on top and positive on the bottom, negative on top, negative on the bottom, negative, right? It could be either one, negative, positive, negative, negative, positive, positive. We don't care as long as they're both some sort of infinity. If your limit is one of those two things, which is called an indeterminate form, then we can find the limit as x approaches a of f of x over g of x by finding the limit, and it is important that you still take the limit as x approaches a of the derivative of f of x over the derivative of g of x. And that is L'Hopital's rule. If I could write L'Hopital's rule. The two things I want to stress. The only time you ever use L'Hopital's rule is when you are finding a limit. Not for any other purpose. L'Hopital goes with limit. They both start with L. So if you see yourself using L'Hopital's rule, it better be because you have encountered a limit. The second thing is that you only ever use it when you have specifically a fraction, a 0 over 0 or infinity over infinity. Anything else where you might think you need to use L'Hopital's rule, you have to do some other stuff first. Okay. So, yeah.
And we can also, it would also be L'Hopital's rule if it's positive infinity divided by negative infinity.
Yep, that's covered right here. Any sort of infinity over any other sort of infinity. Basically, any one of the two types of infinity, plus or minus infinity, over any of the other two types of infinity, plus or minus infinity. It could be plus, plus, minus, minus, plus, minus, minus, plus. So let's look at some examples. Like the limit as x goes to infinity of 6x squared plus 5 over 2x squared plus 1. Now, I bet all of you already know exactly how much this is without using L'Hopital's rule. Show me on your fingers. What's the limit of 6x squared plus 5 over 2x squared plus 1 as x goes to infinity? Yeah, exactly. That many. Oh, not quite. A little bit less. That many. It's okay. Did you subtract instead of dividing? So it's 6 divided by 2, right? Because whenever you have the same degree, it's just the fraction of the leading coefficients. But you could, now you shouldn't, right? L'Hopital's rule is a great tool and you want to use it when we need it, but you don't want to use it if you don't need it. So if I was doing this question, I would probably just say the answer is 3. But if someone said to use L'Hopital's rule, or I wanted to show you that L'Hopital's rule works, well, L'Hopital's rule does work. So we do the limit as x goes to infinity of 6x squared plus 5 over 2x squared plus 1. And here's what I would encourage you to write when you use L'Hopital's rule, right? Equals, and write L apostrophe H over the equal sign. You know what I didn't actually do quite yet that I should have done? I should have checked that I can actually use it. If I plug in infinity, I get infinity on the bottom and on the top. So that is an infinity over infinity type. So I can use L'Hopital's rule. And then the next thing you need to write is the limit. You have to keep writing the limit. And then we can take the derivative of the top part and the derivative of the bottom part. Let's see, the derivative of 6x squared plus 5 is 12x. The derivative of 2x squared plus 1 is just 4x. And now I can actually cancel some stuff. I can say 12x divided by 4x is just the limit as x goes to infinity of 3. And the limit of a constant is just the constant. So L'Hopital's rule totally works here and achieves the same limit, which no matter what method you use, you should always get the same result. Okay, let's look at a couple other examples. So there are some examples where you wouldn't use L'Hopital's rule. Like here's another example where you could do it one of two ways. The limit as x approaches 2 of x squared minus 5x minus 6 over x squared minus 4. Now I want to be super extra clear here. The limit here is not equal to 1. Because it's not, if it would be 1 if we had the limit as x goes to infinity. But this is the limit as x approaches 2. If I plug in 2, I get 4. Oops, if I plug in 2, I'm going to get the wrong answer here because that should have been a plus 6. Sorry about that. If I plug in 2, I get 4 minus 10 plus 6 over 4 minus 4, which is 0 over 0. Which means I could do one of two things here. I could factor and cancel. So I could say, well, this is going to be the limit as x approaches 2 of, let's see, the top factors is x minus 2 times x minus 3. The bottom factors as x minus 2 times x plus 2. And the x minus 2's cancel. And then we can plug in and get 2 minus 3 over 2 plus 2, which is negative 1/4. Or we could have said the limit as x approaches 2 of x squared minus 5x plus 6 over x squared minus 4. Since it's a 0 over 0 type, we can use L'Hopital's rule and say, okay, well, that's going to be the limit as x approaches 2 of the derivative of the top, which is 2x minus 5, over the derivative of the bottom, which is 2x. Here's a good tip. Every time you use L'Hopital's rule, immediately after using L'Hopital's rule is when you want to then try plugging in what x is approaching. So now I'm going to plug in the x is approaching 2, and I'm going to get 2 times 2 minus 5 over 2 times 2, which is exactly the same answer. Definitely chime in if you have questions. I'm going to keep going because there's a few things to say and not a lot of class left. So let's look at another example where you kind of have to use L'Hopital's rule. So let's say we have the limit as x approaches, infinity of x cubed over e to the x, which is an example you may have already seen. You may have seen many of these examples already, but they're still good to talk about because it's important to understand what L'Hopital's rule is. If I try plugging in infinity, what's infinity cubed? Infinity. And e to the x, e to the infinity, infinity. Okay, so it's infinity over infinity. In fact, actually, I'm going to change this up just slightly. Let's make it negative x cubed over e to the x. So it's a negative infinity over infinity. L'Hopital's rule is still applicable. Okay, so we're going to use L'Hopital's rule. Oh, sorry, you can't see that. Yeah. So let's see here. We're going to say, well, great. Let's use L'Hopital's rule. We're going to get the limit x goes to infinity of derivative of the top, negative 3x squared. The derivative of the bottom is e to the x. I still have, if I try plugging in, because that's the next thing I should do, I still have a negative infinity over infinity. So I use L'Hopital's rule again, right? If you still have infinity over infinity or 0 over 0 after you've used it once, do it again. There's nothing else we can do really. So if I use L'Hopital's rule again, limit as x goes to infinity of the derivative of the top is negative 6x. The derivative of the bottom is still e to the x. And if I plug in infinity, that's still negative infinity over infinity. So I do it one more time. With the limit as x goes to infinity of negative 6 over e to the x, because the derivative of negative 6x is negative 6, and e to the x is still e to the x. And now we don't get infinity over infinity. By plugging in infinity, I get negative 6 on top and infinity on the bottom, and negative 6 over infinity goes to 0. Here's an interesting thing to think about. If I asked you all what the limit as x goes to infinity of x to the 1000th power over e to the x is going to be, what do you think that limit's going to end up being? It's going to be 0 because no matter how many times we apply L'Hopital's rule, what's the derivative of e to the x every time? But on top, if you do L'Hopital's rule enough times, probably like 1,000 times, you'll eventually get to a place where the top is just a constant. And even though it's going to be a really, really big constant, like 1,000 factorial, which is 1,000 times 999 times 998, and so on and so on and so on, it's still just a constant. And a constant is always going to get overpowered by something that is getting infinitely large. This limit would also be 0 by repeated application of L'Hopital's rule. But this actually expresses something which is worth noting here, which is that no matter how high a power your polynomial function has, an exponential function will always outpace it eventually. Exponential functions will always outgrow polynomial. Kind of neat. It's actually something that comes up over and over again in math. So it's worth knowing this. More examples. Let's look at, let's look at this one. Excuse me. The limit of x goes to, sure, more infinity, from x squared over the natural log of x. So let's talk about what we think is going to, actually, yeah, we should say that. So first and foremost here, as x goes to infinity, well, x squared certainly does. And the natural log of something, did you have a question? I thought I saw stretching. All right. I saw how. Sorry, I just stabbed my finger where I cut it earlier today with my pen. It doesn't feel good. Ow. Okay, 1 sec. Sorry. Luckily, the Band-Aid was, I'm glad I put the Band-Aid on. It definitely helped protect it, but it didn't feel good. Okay, sorry. So natural log of infinity, not quite. Natural log of 1 is 0. Well, that's the derivative is 1 over x, and you're right, we're gonna get 1 over infinity in a minute when we use L'Hopital's rule. Well, let me ask you all a question. If I was gonna end up using L'Hopital's rule, what would it have to be here? Actually, I have 2 choices. One of the infinities. You're thinking about, so remember, x is going to infinity. Let me draw the graph. Here's the natural log of x graph. And as x goes way, way out to infinity, the natural log graph, although very, very slowly, does go to infinity. So let's see what we get here. Well, I have to use L'Hopital's rule. So using L'Hopital's rule, you get the limit x goes to infinity of 2x on top divided by 1 over x on the bottom. Now, if I try to plug in infinity right now, I get infinity over 1 over infinity, which seems kind of silly. I don't really like that. Although, I mean, you could say I really have infinity divided by 0, which is also going to be infinitely large. But what I would really do here, what is often a good choice to do before you actually try plugging in the next x again, is to simplify your expression. I can definitely rewrite this as the limit as x goes to infinity of 2x times x over 1, or just x. So that's the limit of 2x squared. And for sure, as x goes to infinity, 2x squared goes to infinity. So sometimes infinity divided by infinity is 0. Sometimes infinity divided by infinity is infinity. Sometimes it's something in between, like 5 in our first example, or 2, or whatever it was. So really, when we say indeterminate form, you can literally get any real number value or positive infinity or negative infinity, right? Anything is possible. Oh yeah, let's look at one more before we move on to like a different part of this. Here's a trick question. The limit as x approaches 0 from the right of x squared over the natural log of x. What makes this a trick question? There's no L'Hopital's rule to use here. Or we can't use L'Hopital's rule because if you plug in 0, you don't get 0 over 0 or infinity over infinity. If you plug in 0 to the top, what's 0 squared? Okay. If x is getting closer and closer to 0 on the bottom, what's happening to the natural log of x as x is really, really close to 0? Yeah, right? The graph tells us that as x is close to 0, the natural log function gets really, really close to negative infinity. Okay, 0 divided by a really big number is still 0. 0 divided by anything not 0 is still 0. So definitely when you're finding limits like this, although most of them you'll probably be wanting to use L'Hopital's rule for, make sure that you're allowed to. Right? You have to check and see, do I actually start with 0 over 0 or infinity over infinity? If yes, great, go ahead and move forward with L'Hopital's rule. But there'll probably be one where it'll be like, you can just plug it in and get a real answer. Okay, let's look at some more examples here. Yeah, yeah, sure. Yeah. Question, yeah. No. So the quotient rule should never be in your mind when we're talking about limits, right? So again, this question is not asking us to find the derivative. This question is asking us what this function is approaching as x gets really, really close to 0. But I really sorry to be so adamant about it, but I really just want to just make sure everyone is disabused of the notion that, right, when we're talking about limits, technically you can end up using the quotient rule if you got a quotient in one of your parts, but we're really almost never using the quotient. It's always, if you're using L'Hopital's rule, the derivative of the top part over the derivative of the bottom. End of story. But here we're just saying, oh, well, you've got 0 divided by a big number, so the answer is 0. Okay. Let's look at some things we've seen before, like the limit as x approaches 0 of sine of 5x over 3x. Once upon a time, we would have done this by writing more fractions, right? I would have been, I'm like, do I remember how to do it? Yeah. You would have done this. Sine of 5x over blank times blank over 3x. And then we would have tossed 5x in here and 5x in here. And then the x's here would have canceled. And this would have been 1. You'd have 1 times 5/3. Or we can use L'Hopital's rule, because this limit as x goes to 0 of sine of 5x over 3x is a 0 over 0 type. And so if we apply L'Hopital's rule, so again, when I'm writing the equals with the L' H above it, that means from this limit to this next limit still, right? It's always limits with L'Hopital's rule. It's never anything else. I'm just taking the limit of the derivative of the top, which is cosine of my 5x times the derivative of my 5x over the derivative of the bottom, which for sure is not indeterminate, right? I don't get 0 over 0 or infinity over infinity because the bottom isn't either 0 or infinity. It's obviously 3. And if I plug in 0 for x, I get cosine of 5 times 0 times 5, 3. And cosine of 0 is 1. So I end up getting the same answer I got doing it the other way, which I should get the same answer. It should never be different. Questions about this one? Let's look at one that's a little bit more interesting. This one is, oh yeah, question. I doubt it. You should. So what I would say though is she's posted some practice finals, right? I would definitely look at those and see if it says. But my best guess, and I still haven't looked at the practice finals, is it will probably say evaluate the following limits, and there'll be like 5 of them, and some of them will require L'Hopital's rule, but maybe not all of them. So yeah, and some of them, as we're about to see here, might require some manipulation before you can use L'Hopital's rule, but still have to use L'Hopital's. But no, generally people aren't going to tell you what method to do a thing by often on a map. Not always true, but it is, in my experience, typically true. That no one's going to tell you do it this way or do it that way. You're supposed to be able to look at this thing and go, okay, well, I should try this. That said, at this stage of the game, when we're talking about limits, the majority of the limits you're going to be evaluating will be using L'Hopital's rule. Yeah, let me show you one more. I don't know if she'll ask you one like this, but it's a question I've asked in the past. And the point of this question has been to kind of point out that although you can use L'Hopital's rule, it's not always a good choice to. So here's a limit as x approaches 0 of sine squared of 4x over 7x squared. And it is for sure a 0 over 0 type. So we can use L'Hopital's rule. And I'm going to point out to you that it's probably not the best way to do this. When I used to teach this class back at a different university, I would always ask a question like this to point out to people that L'Hopital's rule is great, but sometimes it's terrible. So let's see, sine squared. So that's really sine of 4x quantity squared. When I take the derivative of something squared, it's going to be 2 times my something to the first power. I'm not going to write the first power. Times the derivative of my stuff, which is cosine of my new stuff, times the derivative of that new stuff. All over 14x. And I would simplify maybe a tiny bit and cancel a 2 here and a 2 here. And so I'm left with the limit, I'm writing the limit every step, of 4 times sine of 4x times cosine of 4x all over 7x. And if I plug in 0, what do I get on top? All right, everybody, let me ask you all a question. Show me on your fingers. What is cosine of 0? Cool. What's sine of 0? Right. So we definitely get 0 times 1, which is 0 over 0. So sine of 0, always 0. Cosine of 0, always 1. We definitely probably need to know that for making sure we're applying L'Hopital's rule incorrectly or correctly. Correctly, not incorrectly. So we need to do it again. So then we're going to have the limit as x goes to 0. And here's where things get kind of garbagey. If you're at the bottom, okay, 7. If you're at the top, we have to use the product rule, and it just gets kind of gnarly. I'm going to just think of the 4 as being factored out in front. And then product rule here, your sine of 4x is cosine of 4x times 4 times the other cosine of 4x. Plus, then leave the sine of 4x alone. And the derivative of cosine of 4x is negative sine of 4x times 4. Which is not impossible, right? This problem is not impossibly hard to do, but it's more time consuming than you want to spend on a problem like this when there's a better way to do it. If we actually evaluate the limit now, we do get 4 times 1 times 4 times 1 plus 0 times 0 times 4 all over 7, which ends up being 16 over 7. But what I would have preferred my students to have done when I was asking them this question was to instead do it like we did this one up here. Break the sine squared up into sine of 4x over blank times sine of 4x over blank times blank over 7x squared, and throw in a 4x right there and a 4x right there and a 4x times 4x to balance those out. And oh, look. The limit of this is 1 times the x's cancel, and you get 16 over 7, which is a lot faster. And you're definitely going to have a limited amount of time on your exam, so you want to be doing things in the most efficient way. So just to point out, if you see a limit that's a power of sine and you're getting like a 0 over 0, I don't know if she's really like prone to asking questions like that, but I know I would ask a question like that. So. I'm not saying I think she's going to. I'm just saying you should be prepared for it. Sure. Oh yeah, I was going to look at this other one. Yeah, I like that one. There's a couple homework type questions just kind of point out how things can be kind of bonkers. How about the limit x approaches 0 of e to the 6x minus e to the negative 6x minus 10x, minus 12x, I think, yeah, sure, over 7x minus sine of 7x. And the point of this problem is to make you do L'Hopital's rule a bunch of times. So I would say you shouldn't actually write it equals 0 over 0 or 2 over. You can, it's totally fine too, but you should really just check. If I plug in 0, I get e to the 0, which is 1, minus e to the 0, which is another 1, minus 0. So I get 1 minus 1 minus 0, which is 0. On the bottom, I get 0 minus sine of 0, which is 0 minus 0. So it's a 0 over 0. And then we can just go straight to applying L'Hopital's rule. So the derivative of e to the 6x is 6 e to the 6x. The derivative of e to the negative 6x is negative 6 e to the negative 6x. And the negative negative will become a positive 6 e to the negative 6x. And the derivative of minus 12x is minus 12. All over the derivative of 7x, 7. And the derivative of sine of 7x is cosine of 7x times 7. And you better believe it, if we plug in 0 again, we're going to get 6 plus 6 minus 12, which is 0, over 7 minus 7, which is so still 0 over 0. So we do it again. The limit as x goes to 0. Okay, the derivative of 6 e to the 6x is 36 e to the 6x. The derivative of 6 e to the negative 6x is minus 36 e to the negative 6x. Derivative of 12 is 0. Derivative of 7 is 0. Derivative negative cosine of 7x times 7 is negative sine of 7x times the derivative inside times the 7 that was still there. And it's still 0 over 0. And finally, I think we can do it one more time and get the limit as x goes to 0 of 36 times 6. I mean, it is 216, but you could just write, and I would encourage you to write 6 cubed, right? We know that's 6 times 6 and multiplied by another 6. Minus, so it's going to be minus 36 times another minus 6, so plus 6 cubed times e to the negative 6x over the derivative of this is going to be negative cosine of 7x times another 7, so it's going to be a 7 cubed on the bottom. And now finally, if we plug in 0, we get 6 cubed times e to the 0 plus 6 cubed times e to the 0 over negative cosine of 0, which is 1 times 7 cubed. Or we get 2 times 6 to the 3rd over 7 to the 3rd. Now put the negative sign out in front. Gross. Anything to say here? No, not really. I mean, you can totally decide as negative 1, 2. But you don't need to do that. What else to say here? I would say that when you're using L'Hopital's rule, the whole idea is that you're checking every time, right? Am I still getting 0 over 0? Am I still getting 0 over 0? Am I still getting infinity over infinity? Not, stop. Yes, we go on. Okay. Let's look at some other. It's interesting in your homework here. Well, we'll get there in a minute. Yeah, we got time. Okay. Sometimes we have things that are not 0 over 0 or infinity over infinity to start off with, like, yeah, let's do that one. Like the limit as x approaches 0 from the right of x times natural log of x, which if we plug in is a 0 times a negative infinity. Now, you might think, and you're not wrong, to think that 0 times anything is 0. The issue here is that we really don't have 0 times infinity. We just write 0 because it's easy to write. What we really have here is a really small number times a really large negative number. And the difference between 0 and a really small number is important, right? If you've got a really small number times a really, really negatively big number, your answer might end up being somewhere in the middle of being small and negatively big. It might be -6. It might end up being 0. It might end up being negative. You literally get anything because just like 0 over 0 or infinity over infinity, this is another indeterminate form. So when you have this sort of indeterminate form, before you can use L'Hopital's rule, you have to make it look like a what? What F word am I thinking of? Not that one, the other one. Fraction. You have to make it look like a fraction. You can only use L'Hopital's rule if you have a limit, because limit starts with L, just like L'Hopital's rule, and it's a fraction. And what kind of fraction? What over what? 0 over 0, thank you. And what's the other thing? Right. So I want to make sure you guys know, like, if you say it to yourself a few times, you're like, oh yeah, it's got to be a fraction. Got to be 0 over 0, infinity over infinity, and it has to be a limit. Okay. So I want to make this look like a fraction. When you have things multiplied together and you want to make it look like a fraction, you always have two choices, and one of them usually sucks. And one of them is usually pretty great. Here are my two choices. One choice is to write this as the limit as x goes to 0 from the right of x divided by the reciprocal of natural log of x. And I guess to someone say comment before, technically here is a place where if we use L'Hopital's rule, we would also need to use the quotient. Because you would do the derivative of the top, which would be 1. And the derivative of the bottom, you'd have to use the quotient rule for the derivative of 1 over natural log of x, which seems terrible. Or we could do it as the limit as x goes to 0 from the right, leave the natural log of x on top, and rewrite the x in the denominator as its reciprocal, 1 over x. And usually the idea here is to make it so that the thing you're putting in the denominator is the simpler thing. So we should definitely be taking this one. This is the one that's going to be less terrible to deal with. I should also point out that when you do this, you will always get something of the right kind of form to use L'Hopital's rule for. Because here I've got a 0 thing times an infinity thing. But when I rewrite it like this, the top is still a 0 thing. And the bottom, well, 1 over an infinity thing is a 0 type of thing. So you have a 0 over 0, which you can use L'Hopital's rule for. Or if we write it this way, natural log of x is still an infinity type of thing. It's actually a negative infinity. And 1 over x, well, if x is getting really, really small, then 1 over a really, really small number gets really, really big. So this is still an infinity over infinity type of thing. So no matter what you do, if you've got a 0 times a type of infinity, and you rewrite it in either one of these ways, you'll either get a 0 over 0 or an infinity over infinity, which means you can use L'Hopital's rule. And then we should make our lives easier. We shouldn't just leave this as 1 over x. We should write it as x to the negative. So I'm going to rewrite this as the limit x goes to 0 from the right of the natural log of x over x to the negative. And now we will use L'Hopital's. And I can, because it's a negative infinity over an infinity. And using L'Hopital's rule, I still have the limit, x goes to 0 from the right, 1 over x on top, over negative x to the negative 2 on the bottom. Okay, here's where you have to be thoughtful. If I'm going to rewrite this in a way that's not helpful, but is kind of helpful. I'm going to do it over here. I'm running out of room. If I rewrite this, I don't like having like one fraction and one negative power. I would rather have them all kind of look the same. So I'm going to write this as 1 over x over negative 1 over x. And here's where I have to be careful, because if I just went and tried to plug in 0, what's going to happen on top? Where's 1 over 0 going to? I should say, where is 1 over 0 going to as we approach 0 from the right? Maybe my hearing is bad. I thought I heard someone say it, which it is. The top is going to infinity, right? 1 over a small number gets really, really big. And the bottom is going to negative infinity. So this is an infinity over infinity type. And we totally could use L'Hopital's rule again. And we definitely should not. Because we can simplify this thing and just take the limits. So when you have powers of x over powers of x, we should for sure rewrite this as limit as x goes to 0 of 1 over x times negative x squared over 1. And then simplify that as the limit as x goes to 0 from the right. 1 over x times negative x squared over 1 is just going to be negative x. And if we plug in 0, we get 0. That's the end of the story. So we do have to have an eye towards simplifying our expression before we keep trying to use L'Hopital's rule multiple times. Let's look at some other examples. Yeah. Let's say we had the following. The limit as x goes to infinity of x squared times sine of 1 over x squared. Which again, I will point out is an infinity times a 0. So we're going to rewrite it. The limit as x goes to infinity. So usually the simpler thing is the thing that's like usually the power of x is the simpler thing that you want to bring to the bottom. So I would definitely rewrite this as leaving sine of 1 over x squared on top and rewriting the x squared here as 1 over x squared on the bottom. Or if you prefer, and I think I do prefer, the limit as x goes to infinity of sine of x to the negative second over x to the negative second. And I will mention that this is a 0 over 0 type. Now, some of you might know the answer to this without using L'Hopital's rule at all. Because we have limit the sine of some stuff over the exact same stuff. And where's that stuff going to? Well, your eventual answer is 1, but where's the stuff that's inside the sine function going to? Wait, if x is going to infinity, what's happening to 1 over x squared? Going to 0. Wait, that sounds familiar. We've got sine of some stuff over the same stuff, and the stuff is going to 0. That limit is 1. Which you could probably get away with just saying is equal to 1. People are usually cool with that. But let's do it using L'Hopital's rule because we should. Now, here's something that I think is really neat when we do this. Using L'Hopital's rule, we still have a limit. If x goes to infinity. The derivative sine of some stuff is cosine of the stuff times the derivative of the stuff, which is -2 times x to the negative third. On the bottom, the derivative of x to the negative second is, bless you, -2 times x to the negative third. Does anything cancel here? Yeah, right? Those two things we took the derivative are the same. Their derivatives are the same, and they for sure cancel out. So then we've just got the limit as x goes to infinity of cosine of 1 over x squared, which for me is easier to see that that's going to be 0 on the inside when I let x get really, really large. For me, it's harder to see that infinity to the negative second power is something that gets small. It just doesn't compute in my brain. I need to rewrite x to the negative second as 1 over x squared so that I know that when I plug in infinity, 1 over infinity squared is super duper small and getting closer and closer to 0. I'm not saying you have to rewrite it that way. I'm just saying that's the way I can see it. That's the cosine of 0, which is what we said it was. So this is the other way of doing it. Yeah. We said 1 in the beginning because right here we had the limit as some stuff goes to 0 of sine of the stuff over the same stuff. And we saw a lot of examples weeks ago where we know that that kind of thing is always equal to 1. Right, but the stuff is still the same, right? And the stuff is going to 0. Right. But it's just kind of, that probably won't come up, but it is a pattern that sometimes pops up. I have one other one. Oh, sure, yeah. What's time? Okay, let's look at, here's another one that's kind of, I don't want to say obvious, but limit as x goes to infinity. Yeah, I would ask this question on a test of x squared times e to the negative 3x. We should always think about plugging it in. If I plug it in, x squared is certainly an infinity as x goes to infinity. And e to the negative 3x, if x is going to infinity, e to the negative 3x is going where? Other side. Right? E to the negative 3x goes down from left to right. Or if you prefer, no, that's not helpful, James. Yeah, it is 0. Because e to the negative 3x looks like this. Now, this is the one exception where you don't bring the x to the power down to the bottom part, you bring the e to the stuff down to the bottom part. Because the e to the stuff is always going to have a nicer derivative than x to the whatever. So here we're going to rewrite this as the limit as x goes to infinity of x squared. You could write 1 over e to the negative 3x, but don't make your life hard. Write it as the limit as x goes to infinity of x squared over e to the positive 3x. It is much nicer to apply L'Hopital's rule to. It's still an infinity over infinity type, or I should say it's become an infinity over infinity type. And we should already have an idea of what's going to happen here, because we know that exponential functions are always going to outgrow polynomial functions. So since the denominator here is eventually going to overpower the numerator, we would expect this limit to be 0, because the denominator is going to outpace the numerator for sure. But we should still show the 2 iterations of L'Hopital's rule. Here to the top is 2x. Here to the bottom is 3 times e to the 3x. We still have an infinity over infinity. So we're going to use L'Hopital's rule again. Here to the 2x is 2. Here to the 3e to the 3x is 3e to the 3x times another 3, the 9e to the 3x. And now you have 2 over something infinitely large. It's going to be 0. I'm moderately surprised she didn't have any questions of the exponential forms. I just want to double check I'm not like missing something here. No, I don't see any. Okay, so
Power of like the power of x.
well, that is an exponential function, but an exponential. So there are 3 other. So actually, there's 4 other indeterminate forms we could talk about. Let me show you one of them because this one is in your homework. So here's another different type of indeterminate form. So far, here are the forms we have. There's 0 over 0. There's infinity over infinity. There is 0 times infinity. There's also what we're about to talk about, which is an infinity minus infinity. Again, none of these things actually mean what I've written. When I write 0 over 0, what I really mean is a really small number over a really small number. Infinity over infinity is a really big number over a really big number. And infinity times 0 is a really small number times a really big number. And infinity minus infinity is a really big number minus another really big number. And for the infinity minus infinity, the signs do matter. It's a positive infinity minus a positive infinity. Because if you had infinity minus negative infinity, that wouldn't be indeterminate. That'd be infinity plus infinity, which is still infinity large. There's nothing to see there. And in a similar way, if you had negative infinity minus, oh my gosh, brain, infinity, that would just be negative infinity because you're getting more negatively infinite. So when you have an infinity minus infinity, the types of infinities have to be the same sign so that they actually are being indeterminate. Don't worry too much about it. So let's look at an example of that, and then we'll talk about the other 3 forms. The limit as x approaches 1 from the right of 1 over x minus 1 over natural log of x. So here's what we've got. If x goes to 1, well, 1 minus 1 is a little bit close to 0, and 1 over 0 is going to be infinitely large. And it is a positive infinity because that denominator is very slightly positive. In a similar way, if x is a little bit bigger than 1, then the natural log of x is just a little bit bigger than 0. So we still have a 1 over a slightly positive number. And this is also going to be a positive infinity. So we have infinity minus infinity, which we would love to apply L'Hopital's rule. So here's where Here's where we need to be extra careful. Can I use L'Hopital's rule yet? Probably not. If I could, I probably would have done it by now, right? No, I can't. Why not? What don't I have? Right. Now, some people might say, well, James, you kind of do have a fraction. And you wouldn't be wrong to say that. But I don't have the right kind of fraction. Right? I don't have a fraction that is a 0 over 0 or an infinity over infinity. More importantly, I should say I really just need one fraction. Right? We can't have more than one fraction. Otherwise, you can't really use L'Hopital's rule. So to get one fraction, we're going to get a common denominator. So I'm going to say, well, this is going to be the limit as x approaches 1 from the right. I'm going to multiply this by natural log of x over natural log of x. And this one by x minus 1 over x minus 1. And so when I put this all together, notice, right, I'm just simplifying right now. I'm not writing L apostrophe H anywhere because I'm not using L'Hopital's rule yet. I'm just rewriting this expression as, well, my denominator is the natural log of x times x minus 1. And the numerator is the natural log of x minus what? Minus x. And then what? Close, but not quite. Actually going to be plus 1. Because that fraction, the numerator of that fraction, when you're in the numerator of a fraction, there's a minus sign out in front, you kind of got automatic parentheses around you. And so we have to distribute that minus sign to the x minus 1 and get a minus x plus 1. Here's how we also would have known. Let's say we didn't do that. And now we check to see if we can use L'Hopital's rule. What's natural log of 1? 0. Right? Natural log of 1 is 0. Right. Natural log of 1, yeah, 0. So 0 minus 1 minus 1. What's minus 1 minus 1? Negative 2. And the problem is, if I've got an indeterminate form here and I'm just rewriting it, it should still be an indeterminate form. But I'm getting minus 2 over 0, which is not an indeterminate form. That's just some sort of negative or positive infinity. So noticing that I didn't get the right thing, I didn't get 0 over 0 or infinity over infinity. I'm like, oh, I must have made an algebra mistake. And I did. I forgot to distribute the minus sign. Because now if I distribute the minus sign, I get a minus x plus 1. Now I do have a 0 over 0 indeterminate form. I've got 0 minus 1 plus 1, which is 0, over natural log of 1, which is 0, times x minus 1, which is also 0. So that's a good check. If you're rewriting something that we think we need to use L'Hopital's rule for, once you've got to the place where it is a fraction, if you then check and it doesn't end up being 0 over 0 infinity over infinity, make sure your algebra is correct, right? Because it's easy to make a little mistake like that. So now we're going to apply L'Hopital's rule because we have a 0 over 0. Still a limit. There's always going to be a limit until you actually get the number that's the answer. All right, derivative of the top. We got a 1 over x minus 1 plus 0. Derivative of the bottom, have to use the product rule. This is going to be the derivative of the natural log of x times x minus 1 plus natural log of x times the derivative of x minus 1, which is 1. And my gut says it's probably still going to be 0 over 0, but let's check anyway. On top, if I plug in 1, I definitely get 1 minus 1, which is 0. On the bottom, if I plug in 1, I get 1 times 0 plus the natural log of 1, which is also 0. So I do get 0 over 0. So I keep using L'Hopital's. Okay. And now we take the derivative of the top again. Ooh, what's the derivative of 1 over x? Exactly, negative x to the negative 2. Or if you prefer, negative 1 over x squared. Either way is fine. I definitely, I don't know. I like negative x to the negative 2 when I know I have to take more derivatives. I like negative 1 over x squared when I know I have to plug values in. You can always go back and forth, right? You can write it either way, but sometimes you're like, if I'm not good, like if this was 1's fine, but like if I was trying to plug in 0 here, what's 0 to the negative 2 power? What's 0 to the negative 2? Oh, a better question. What's 1 over 0 squared? Right, it's undefined. But notice how much easier it is for me and probably for you to see it this way and not that way. That's why it's good to be able to go back and forth. Right? Sometimes to the -2 power is great, but sometimes 1 over something to the second power is easier to see what's happening. Okay, on the bottom, I should have simplified the bottom first. I really should have simplified the bottom first. Let's actually do that before we do this. So the bottom here would have been 1 over x times x is 1. 1 over x times -1 is -1 over x, and natural log of x. That's much better than using the product rule again. The derivative of 1 is 0. The derivative of -1 over x is positive x to the -2nd. And the derivative of natural log of x is 1. And now I definitely write it. I'm a sucker. I would write this as the limit as x goes to 1 on the right of -1 over x squared over 1 over x squared plus 1 over x. And then we can plug in. And you get -1 over 1 over 1 over 1. I don't know why I'm writing 1 over 1. You shouldn't write 1 over 1. If you find yourself writing 1 over 1, stop and just make it a 1. Because 1 over 1 is 1. So we end up getting -1 over 1 plus 1, which is -1. So in this case, infinity minus infinity was -1/2. This infinity was 1/2 bigger than that infinity, which seems like a weird thing to say and not something we really say, but it feels funny to say. So here's the question I have. And we're definitely gonna do this one example either way because you should see it. But then if the answer is no, then we won't do any more. So did your teacher talk about or mention any limits like this? The limit is x goes to infinity of 1 plus 1 over x to the infinity of power. Oh my gosh, James, slow down there. Oh my God. Let me try that one more time. Limit is x goes to infinity of 1 plus 1 over x to the x power. It's okay if the answer is no. Judging from the homework, it looks like she might not have ever said anything about this. Okay, I want to show you this one example because it's kind of important for your mathematical general knowledge, I think. But then we'll move on. But what I want to point out is this is also an indeterminate form. If you plug in infinity for x, 1 plus 0 is a 1, and the x going to infinity is an infinity. And 1 to the infinity power isn't really 1 to the infinity, right? It's a number that's close to 1 being raised to a really, really large power. So if you took like 1.00001 and multiplied itself by like a billion times, it wouldn't be 1. It would move far away from 1. So let's see what happens here. How do I want to do this? Yeah. So here's what we're going to do. We're going to say that the limit, yeah. No, but again, that's why I want to point out this is not 1. It's really slightly larger than 1. Sorry, my writing is atrocious there, but that's the idea, right? Just like before, you didn't really have 0 times infinity. You had a very, very small number of times infinity, which could have been anything. Here you have a number that's just a little tiny bit bigger than 1, raised to a really, really big power. Okay, so what we're going to do is we're going to look at the limit as x goes to infinity. And yeah, you should write this. E to the natural log of 1 plus 1 over x to the x. Or as you might see some people write in the future, exp. Some people write this, exp of the natural log of 1 plus 1 over x to the x. If you ever see this exp notation, it literally just means e to the power of. It's just a way of writing it so you don't have this kind of exponent that is smaller in some ways and harder to read. All right, so now we're going to do a couple things. I'm really just going to focus on the exponent here. The e is just kind of coming along for the ride. So this is going to equal the limit as x goes to infinity of e to the power of, that x can come down in front of the natural log using our regular natural log rules. Of x times the natural log of 1 plus 1 of x. And I'll point out that now, if x is going to infinity, I have an infinity times a 0. Because 1 plus 0 is 1, and the natural log of 1 is 0. And then we're going to do one more rewrite. We're going to write this as the limit as x goes to infinity of e to the power of the natural log of 1 plus 1 over x divided by the reciprocal of 1 over x. Sorry, the reciprocal of x, which is 1. Are there any, well, actually, before I say that, and now I just point out, now we have that this part up here is really a 0 over 0. If x is going to infinity, 1 over infinity is 0, 1 plus 0 is 1, natural log of 1 is 0, and the bottom is also a 1 over infinity. Before we do the next part, let me just backtrack for a minute and ask any questions about any of the things that I've done so far. Happy to clarify. Everyone's cool with the fact that I changed this into e to the natural log of that? Right, it's definitely right because where's the chalk that usually is right there? It's on the other side. So to remind everybody, right? We've definitely seen before that e to the natural log of whatever is just the stuff. That's why I was able to do that. So I went from here to there. Okay. Well, now I've got a 0 over 0, and even though it's in the x1, I can still apply L'Hopital's rule. I'm going to say that this is equal to the limit as x goes to infinity of e to the power of, okay, the derivative of the natural log of some stuff. Let's zoom in here. The derivative of the natural log of some stuff is 1 over the stuff, so 1 over 1 plus 1 over x, times the derivative of the stuff. The derivative of 1 is 0, and you all just told me like 2 times the derivative of 1 over x is negative x to the negative second. Okay, and on the bottom, the derivative of 1 over x, again, is negative x to the negative second. And just like in the problem we did a couple times ago with the sign of whatever, those cancel out really nicely. And now we're left with the limit as x goes to infinity of e to the power of 1 over 1 plus 1 over x. And now we can evaluate this. 1 over x goes to 0, and we just end up getting e to the 1 over 1 plus 0. I want to point something out because I haven't said this, and I wanted to make sure you guys have seen it. After I plug in x and I get numbers and there's no more variables, I don't write the limit anymore. Right? After you evaluate the limit, even though I haven't simplified it yet, you should stop writing the limit. So then I get e to the 1, which is now one more word about this, and then we'll stop talking about this. I want to point out this is a pretty famous limit. This is actually how e is defined sometimes. So it is true, and now you've seen actual real proof that e is equal to the limit as x goes to infinity of 1 plus 1 over x to the x. Which kind of looks like the compound interest formula if I lent you $1 and charged you 100% interest and changed the number of times I was compounding it to more and more and more. This is actually the continuous compounding interest formula. All right, so just to kind of back it up, you didn't see any examples like this, right? Like there's none of this in your class for sure. Okay, so I would say you don't need to spend time thinking about this. I'll double check the practice exams finals just to see if there's anything like this. But if she didn't talk about this in class, even though it's a very kind of valid thing we do with L'Hopital's rule, I would say you probably don't need to worry about it for your finals. Okay, it's 2:45. What else should we say here? What else do I say about L'Hopital's rule? Anything? Yeah. So I'm thinking we'll go over practice exams on Thursday. Yeah. Because we still should probably spend these last 15 minutes at least briefly talking about optimization, because we haven't talked about optimization at all. But yes, Friday can be a day where we go over anything. Thursday, we can go. We can go over the practice exams. We can dedicate all the practice exams. We can answer any questions you want me to answer. You should just come prepared to ask questions, and I will certainly be prepared to answer them. I will come with the practice exams and be like, we can just go over them if you want. but we can also do other questions if you have other specific questions, like from the homework or whatever. All right, so let's look at optimization for just a minute. So optimization is kind of the other side of word problems. If you see wordy problems on your exam, it's usually one of two things. It's usually a related rates problem, where they're going to tell you, you know that something is changing in some way at some rate, and you want to find that the rate this other thing is changing at. Or it's going to be an optimization problem, where they're going to tell you something like, we have some sort of thing with this, with a limited amount of surface area, or it needs to hold some volume, or is closest to some other point, and you want to know what's the dimensions or the point that minimizes or maximizes the thing they're asking about. So if you're thinking optimization, somewhere the words maximize the volume, minimize the surface area, find the box that is the biggest by volume, that kind of wording should appear to indicate, oh, this is an optimization problem. So here's an example. A rectangular box with a square base and no top is to be constructed so that the surface area is 108 square inches. What dimensions will maximize the volume of this box? Now, something else to be aware of with these questions, usually the question is asking for one of two things. It is either asking for the dimensions or the numbers that will maximize the thing, or it's asking for the actual maximum value. So I could ask for the dimensions of the box. I could also ask for what's the volume of the biggest box. Be careful when you read the question, because it's usually one or the other. It's not typically both, although it can. Someone could ask for both. Someone could ask for the dimensions and the maximum volume. All right, usually with these problems, not always, but often, you want to draw a picture. I'm going to draw a rectangular box with a square base. And I've happened to draw mine so that it looks like it's taller than it is wide, but you could draw it really short. There's my box, and it has no top. I'm a fan of, well, back it up. I was about to start writing some equations. I haven't labeled anything. So definitely make sure you label things you're using. I think actually a number of people have come to me and said they missed a point on the problem on the second midterm, where you had to do the intermediate value theorem thing because you didn't write the f of x was equal to the function, right? That's just a not labeling a thing kind of issue. So it's important to, when you're saying a thing is a thing, to actually say the thing is equal to the thing you want. And it's perfectly fine to be like, let f of x equal this, or I'm going to call this side x. And this side I'm also going to call x because they told me it was a square base. And I should never be using more variables than I need to be using. Right? If they say the base is square, then this length and that length are the same length, and they should have the same. A lot of the time in these problems, you're going to end up trying to maximize or minimize a function of two variables. Here, the volume is equal to x times y. But we don't yet have the tools to maximize or minimize functions of two variables. That's something we develop later in 17B or 17C, I don't know which. So here, we also have to use the fact that we have a constraining piece of information. Our constraint is that the surface area is equal to 108 square inches. Well, we need to come up with an equation for the surface area. For boxes, it's really, really easy. It's just the areas of all the squares or rectangles that make up all the sides. So the surface area is, well, the bottom side is x times x. And then this front face here is x times y. And this side face is also x times y. And the back face is also x times y. And the left-hand face is also x times y. I've got 4 x times y's. And if it was a closed top box, I'd have another x squared, so I'd have 2x squared. But it's an open top box, so I only have 1x squared. And that is equal to 108. Usually, in these sorts of problems, the thing you're trying to optimize shouldn't equal a number. If it did, then you would know what the value is. The thing whereas your constraint should be equal to some number. So I'm going to take this constraint, and I'm going to, this is my constraint here. I don't want the surface area right there. And I'm going to solve for either variable. Solve for x or y. Your choice. Choose the choice that is easier. Sometimes either way, like sometimes you'll have like x plus y equals 10, and solving for either one is simple. Here, there is definitely a right choice and a wrong choice. I want to isolate y, because there's only one y there. It's easy to get by itself. Isolating x would require the quadratic formula. I don't want to use the quadratic formula. You don't want to use the quadratic. Nobody wants to use the quadratic formula. So here, I'm going to say that 4xy equals 108 minus x squared, and then divide both sides by 4x. So y equals 108 minus x squared divided by 4x. And with that, I'm going to take that and then substitute it back in for y in my volume equation. So now I'm running out of room here. My volume equation, which was x squared y, is going to become volume equal to x squared times 108 minus x squared 4x. Great. Now my volume function, instead of being a function of two variables, is a function of one variable. And how do we maximize or minimize a function of one variable? Right, because we're looking for what? Well, but the things before we find them in tonight, you're right, but we're looking for the critical points. That's what we're finding, but that's exactly what you said, Maggie. We're setting the derivative equal to 0. That's how we find the critical points. Technically, we should also look for where the derivatives are defined, but that's usually not going to come up in these sorts of optimization problems. I should not be doing it like this. I should not try to be using the product and the quotient rule. I should simplify this expression first. And I can really easily. And x cancels here and here. So I can rewrite this as volume equal to x times, I should also think of this not as 108 minus x squared over 4, but 1/4 times 108 minus x squared. I'm going to distribute the x because I don't want to use the product rule. But I'm not going to distribute the 1/4. I'm going to leave that 1/4 multiple up in front. I'm going to have 108 times x minus x cubed. That is the best way to do it. Make it so your function is only kind of one thing. I don't want a product rule situation here, but the 1/4 constant can stay out. It doesn't have to. You could distribute it if you really, really wanted to. I just don't want to. So then we're going to take the derivative. The derivative here, the 1/4 constant hangs out. The derivative of 108x is 108. Derivative of x cubed is 3x squared. And what are we setting this equal to? Yeah. I like factoring, but you can do whatever you want. Factor out of 3 here. Okay, what can I factor? Yeah, you get 36. I can divide by 3. 108 divided by 3 is 3. So I can write this as 3/4 times 36 minus x squared equals 0, or even more, 3/4 times 6 minus x times 6 plus x equal to 0. All right, let me ask you all, what are my critical values? 0 is not a critical value. Okay. Which of these critical values make any sort of sense in the context of the original problem? Only positive sense. That x equal to -6 is meaningless in this situation. Sometimes you might have to check that it's actually a maximum. So if I wanted to check this was a maximum, I would quickly throw it on the number line. Now, I'm gonna stop at 0 because x shouldn't be negative. So I don't want any of that over there. But positive 6 is still a critical value. And I'm looking at what's happening when I plug into f prime. By the way, this idea here of testing to see if it's actually maximum or minimum is why I factored like this. I could have solved this a different way, right? We could have said like multiply both sides by 4, 108 minus 3x squared equals 0, 108 equals 3x squared, x squared equals 36, x equals plus or minus 6. You could have solved it that way, but then when you're testing points here, you don't know what the derivative is based on having solved it this way. Whereas if you factor your derivative and don't actually like change the derivative, you just rewrite it in a different way, then you can say, oh, if I plug in 1, 6 minus 1 is positive, 6 plus 1 is positive, and a positive times a positive is positive. So my function is increasing. And if I plug in 7, 6 minus 7 is negative, and 6 plus 7 is positive. Negative times a positive is negative, it's decreasing. And oh yeah, we definitely have a maximum at x equal to 6. But we're not done, because the question said to find the dimensions, plural. There's more than just x, there's also y. Fortunately, and this is almost always the case, you should have an equation for what y is equal to, right? We literally had an equation for y was equal to help us figure this out. So looking back here, I see, great, there's y. Y equals 108 minus x squared over 4 times x. So if I plug in x equal to 6, I'm going to get 108 minus 6 squared over 4 times 6, which is 108 minus 36, so 72 over 24. So those are my dimensions. X is 6 inches, y is 3 inches. For problems like this, you probably at the very, very end should tack on whatever the correct units are. Right? Right? It was inches, right? Yeah, inches. You don't have to carry the inches through the whole problem, but definitely at the very end, like if they said what are the dimensions, you should use like x equals 3 or x equals 6. Oh, x is 6 inches, y is 3 inches. Okay, I could try and squeeze in another problem, but I think we should just. So Thursday we will review final exams. We can certainly do more optimization problems. We can do kind of whatever is on there that you want. Then, yeah, for those of you who have your exam on Friday, what time is your exam on? Who has the exam on Friday? What time is it on Friday? 10:30. Okay, yeah. Yeah, I think Grant will be dropping at 9, but if that really, you should have stopped studying by 9 a.m. Like you don't want to be studying up until the last minute, right? Like night before, study as much as you need to. Try to go to bed at a reasonable-ish hour. And I will remind you of this on Thursday when I see you the day before your final. And then for those of you who have your exam on Thursday, I'll see you all next week. And you have much more time to study for this. All right. I'll see you all on Thursday.